We're going to balance using the algebraic method. First, start by putting down coefficients as variables a, b, and c. The reason for a, b, and c is we have 3 chemical species involved. If you have more chemical species, obviously you will use more of the alphabet for your variables. Then create linear equations for each of the atom types involved, counting up the number of that atom associated with whichever variable or coefficient it belongs with. We've done this for aluminum, 1A equals 2B. For oxygen, 3A equals 3B and 1C. And for hydrogen, 3A equals 2C. Then choose something to be set equal to 1 and then solve for the other variables. The criteria is to choose the one with the highest coefficient and tells you the most about the other things. I've chosen B. B set equal to 1 tells me that A equals 2. Through substitution method, I can solve for C. We'll show it using the wrap table method as well. This is very much like the algebraic method as far as the linear equations go. It just excludes variables and it adds up all of the locations that an atom appears. Notice oxygen added up to 4 on the product side, even though it occurs in 2 locations. Then, using a teeter-totter sort of seesaw back and forth balancing method, try to balance out all of the atoms by putting in coefficients next to each chemical species. I went after the aluminum first. This caused me to double everything on the reactant side, and then I made adjustments to balance for oxygen and hydrogen. Sometimes we start with questionable amounts. You can see that my question mark went away. The reason it was there was we assume that there must be 1 aluminum oxide in order for everything else that I've balanced to be true. Here we're going to look at the wrap table versus the linear equations and see that they're virtually the same. There's 1 aluminum on the reactant side, 2 on the product side, with oxygens 3 on the reactant side, 4 on the product side, even though it occurs in 2 locations. If you add those 2 locations together, you'll see that it is still 4. And then with hydrogen, 3 on the reactant side, 2 on the product side. It's very easy to see that these are the same thing when an atom occurs only in 1 location on a given side. It's a little more challenging when it's broken down and shows up in multiple locations on a given side.